So in this problem we have this cylinder being propelled up by this rotating rod here. We're given the speed that this rod is rotating. We're given the weight of this object we're moving. And they want to know what is the force that this lever puts on that object at the instant that our angle is 45 degrees. So I'll have that rod, I'll have the horizontal, and that rod is at 45 degrees. And we also have that vertical wall with our object really in between them. So because we're given thetas, angular speeds and all this stuff, I'm thinking that the cylindrical coordinate system, that polar, that radial transverse approach, is the way to go here. So I know that our angle will be increasing this way. So this is going to be my transverse direction, that theta direction. And this right here, this is basically our R. This is the origin right here, which makes this right here our radial direction. And since they want to know force, I know I need to start by figuring out acceleration. A lot of these dynamics problems can be broken down to this. It's either you're asked to find force, which means you need to start with acceleration and work your way to force, or the other way around. They give you the forces and you're asked to determine what type of motion is happening, whether it be the acceleration, velocity, or position, any of those descriptors of motion. So I know my main operating equations will be these. Alright, so let's think about what forces are happening. Well, we have this rod that is creating the motion. So that rod is going to be contacting our object with the normal force. Let's call this normal force from the arm. We have the wall. The wall is always going to be putting a normal force this way, so normal force from the wall. And of course we'll have the weight. We know the weight to be 4 pounds. That's really all that's touching this object. So we need to figure out my two acceleration components. But I know with these cylindrical coordinate system type of problems, it's usually a good idea to start with velocity, because it contains some of the symbols, quantities that we may need. So I start thinking about velocity, and I notice something about this motion. Really, I already know the direction of the velocity of this object. The velocity is going to be up, like this. That is a fact. And so this is one of those problems where you can actually go through a lot quicker because we already know the direction of the velocity and the acceleration. Velocity is going to be up, clearly. As this thing rotates, that object's going to be forced up. The acceleration can either be up or down. So really we know its sort of line of direction, and we can leverage this. So if I just make a separate diagram to focus on my kinematics, my A, my V, and my position, I know that the true velocity will be going up, and I know we can split this velocity into a transverse component and a radial component. And of course these components form a right triangle. And since this is a right triangle, we can use that. If I know this angle right here, if I can figure that out, that means to unlock all the quantities, all the sides of this right triangle, all I need is one of the sides. All you need is one side and an angle, and you got it all. So if I have a 45 here, I'll just draw a really quick horizontal right here. This is going to be 45. 90 minus 45 gets us another 45. And we have one more right angle right here. 90 minus this 45 gets us a 45 right here. So it's all going to be 45, long story short, because 45s are special like that. But, of course, with different angles, you'd work through that geometry. So I'm going to put a little line here to symbolize that they're both the same angle of that 45. So, now that I have that angle, which side should I figure out? I think this one's the one I want to go for because they give us how fast the angles are changing, the angular speed, and I know we can figure out this r no problem. Because this length right here is 4 feet, and therefore this guy right here we can calculate by using cosine. The cosine of that 45 right here will equal the adjacent over the hypotenuse, which for us is that r coordinate. We'll calculate that to be a 5.66. So let me write some information down. We know that the angular speed is a 1.5. And we know that the r at this instant is a 5.66. Units are in feet. So with our r known and our theta dot known, we can calculate that transverse component, and we'll get an 8.49. And since this is a component of velocity, just a smaller part of velocity, this is going to be in feet per second. So knowing that now, I can work that right triangle up there. I can do the tangent. The tangent of that 45 is going to be the opposite over the adjacent. And tangent of 45 is just a 1. So we know that this side of the triangle will be the same length. So our VR, aka the theta dot, will equal that 8.49. And you always want to be checking your signs just to make sure. Remember, r dot really just means at this instant, given a tiny change in time, what is that corresponding change in r? What is this ratio of change, rate of change? Should it be a positive? Well, yes, it should, because as this thing continues to rotate, look at how those r lengths are getting longer. So yes, this should definitely be a positive. This number should as well, because our angles are increasing with time. This thing is rotating this way, our angle is getting bigger at this moment. So I recommend always, once you get those numbers, just do a check, make sure it supports the visualization of the problem. Now, just in case you weren't able to leverage this right triangle here, that is to say, just in case this wasn't a nice problem in which we already knew the directions of our velocity and acceleration, of course you wouldn't be able to do this, and you'd have to do it another way. So what you would have to do is this. You'd have to make some equation that in a sense gives you the path of this particle in terms of r and theta. So in this case, I'd be dealing with this right triangle. And I can write that the cosine of 45 is equal to 4 over, well actually really, the cosine not of 45 but of theta. And I'm saying theta because I'm going to take the derivative. I'm basically going to take the derivative of this equation. And of course, this number that goes in here is not a constant with time. So cosine of theta is equal to 4 over that r. I can get r by itself. And that comes out to this. Don't forget, when I bring this r over here, and I divide this cosine over here, don't forget, 1 over cosine is secant. and I would want to take the derivative of this equation. And what that would get for me is the instantaneous rate of change of r with time. And I have to go through the calculus of that. 4 is a constant. Gotta watch out for the chain rule here. Have an equation inside of an equation. Theta is technically going to be an equation. Some equation with respect to time, or something like that. And of course, so that's the inside equation. And of course we have the outside equation, the secant of that theta equation. So again, chain rule is at play here. So the derivative of the outside is the secant theta tangent theta, and the derivative of the inside would be the derivative of whatever this equation is. So I write that, the derivative of that equation. So 45, 45. We know that our angular speed is 1.5. So therefore, we would know our r dot, and with the r dot known and this known, we could do the Pythagorean theorem, recognizing that the true speed squared is that hypotenuse, and that the components are just legs, the other sides of this right triangle. So this would be the other way to work it out, and this is what you usually do if, you know, we can't say that the velocity or the acceleration is in a known direction. So we'll just map this out real quick. Yep, I'm getting that same 8.49. So here's our 8.49. This is also 8.49 from that multiplication. And we would run that Pythagorean theorem, and we would get 12. But of course, we can do this from the geometry. Here's our unknown hypotenuse, velocity magnitude. We got that guy, 8.49. We got this guy, 8.49. Here the angle is a 45. So I can use tangent, sine, really whatever I want. Well, not tangent. We'll do that the sine of that 45 is equal to the opposite over the hypotenuse, and we'll calculate the hypotenuse, and again we get that 12. So all in all, usually if you know that velocity direction, that acceleration direction, you can just leverage the geometry and create a nice vector component right triangle without having to go through the calculus and the derivatives. But if you don't have this, you'll need r as a function of theta, and you have to do your derivatives in order to calculate enough of these guys to use your Pythagorean theorem. And of course, this Pythagorean theorem works no matter what this angle is. Alright, hope that's making sense. If it doesn't, of course, just post any questions you may have. So we're determining that our true velocity, or true speed, is a 12. So now I'm really done with the velocity. I can move on to acceleration now. Really, we have a very similar picture. I'll just assume that the acceleration is that way. Here's my transverse component and my radial components of acceleration. So maybe let's start with this one and see if we can figure it out. I know that the acceleration of the variable theta, that is the change in my angular speed. So just make sure you really can visualize what this idea means. This right here is a theta double dot of 0. I'm moving in a nice constant speed. So this number is going to be some constant, like 2. And since it's not changing, that means the change, or theta double dot, of this is 0. So actually come right out and tell us, a constant clockwise angular velocity. So that will indeed be a 0. We have r dot, and we have theta dot. So we can actually calculate this out. Be 2 times 8.49 times 1.5, and that will be a 25.47. So now that we know that, I'm tempted just to use our right triangle like we did for the velocity. But it's making me a little uncomfortable that really we don't know if that acceleration is up or down. This would be acceleration up. We accelerated up. But this, slowing down, would be acceleration downwards. I mean, who's to say what it is? And if our acceleration happened to be down, let's just see how that would affect that triangle. So it looks like the angle would be the same. It would still be that 45. So technically, since I know the side right here, I could figure out these sides. But the thing there is, how do I know what direction it is? That sine, cosine, tangent stuff, it's just going to give me numbers. It's just going to give me sides of right triangles. And actually, I just realized something. Kind of had a dumb moment there. I got a positive number for this, which means that that component must be in the positive theta direction. So basically, we just proved that the acceleration is up. So we now know that the acceleration is positive because we're getting a positive number for our transverse component. So therefore, this purple component is in that positive theta direction. So now I'm just going to go straight for the true acceleration, because that's really what I want to figure out the forces. And I'm thinking to myself, you know what, I really don't need this. Because I know that true acceleration's direction is really only in the upper or positive y, how about I just do sum of forces in the x and the y? Because we know the direction of this acceleration. Of course I could do this, but to do that I would have to figure out that radial component to use that equation, and I don't really have to. So the cosine of that 45 will equal that adjacent over the magnitude of the acceleration, which we've now proven to be in the positive y. We'll crunch that. We'll get a 3602. So I will write that. Acceleration is a 3602, and we know the direction is purely upwards. Now with that, I'm just going to change gears a little bit. I'm going to change our coordinate system to an xy. Y will be positive up. X will be this way, just a conventional coordinate system. So I'll erase this. If I sum the forces in the x, because my object is only going upwards, the x component of velocity is 0. So the whole right-hand side of Newton's second law will be a 0. And the sum of the forces in the y will equal the mass times that positive 3602. So now we just got to break down our vectors into components. Really, this is the only one I have to break up. So I know I have that 45 right here, and here's another 45 because of that 90. So let's see if I can go straight for some forces in the y. I got a minus weight, and I have a plus that sine component of that normal force from the arm. So normal force from the arm times the sine of that angle, and it's positive, must equal the mass, which is the weight divided by the gravitational constant. And I ran out of room, so here is that, pretend I wrote that 3602. And we can just solve for the normal force of the arm. And we're getting a positive 11.98. Alright, an interesting problem. Kind of liked how there were a couple forks in the road there. We could have figured out the velocity via the calculus or via the geometry. And I could have continued, gotten my radial acceleration, and done the some of the forces in the in the radial and transverse like I had planned to do initially. And I'm sure we would have gotten this answer. So different ways, there's always different ways you can do it. If you have any questions, please ask them in the comments.